Good morning and thank you for attending this presentation. My name is Nikolaou and I'm a student at the National Capodician University of Athens. Today I will present the system-level architecture and subsystem design of a small high-power sounding rocket. The scope of this work is vehicle integration, specifically how the major subsystems are defined, interfaced and bounded by explicit engineering assumptions. I will summarize the design rationale behind the vehicle architecture, the analytical methods used to define load environments and interfaces, and the verification strategy adopted to reduce risk prior to flight. The emphasis is on clear load paths, predictable subsystem interfaces, and stability, rather than peak performance optimization. The objective is to establish a coherent engineering baseline that can be incrementally validated through static test, ground-level subsystem testing, and staged flight campaigns. The mission objective is to build a reusable sounding rocket for low-altitude experimental flights that can be repeated frequently under controlled conditions. A target apogee on the order of 1 km constrains the flight envelope to subsonic and high subsonic speeds, reducing aerodynamic and thermal uncertainties while remaining technically meaningful. The mission prioritizes repeatability, operational safety, and measurable outcomes over maximum altitude. This envelope supports disciplined iteration, define requirements, build a prototype, test the highest risk functions on the ground, and then expand the flight envelope only after evidence supports it. Success is evaluated by stable behavior and recoverable hardware rather than a single maximum altitude attempt. The chosen envelope aligned with practical constraints, launch site rules, and recovery area limits. The vehicle is a single-stage, unguided sounding rocket with an overall length of approximately 1 meter and a diameter of 40 millimeters. The lift of mass is approximately 1.5 kilograms, which constrains the motor selection, structural sizing, and recovery hardware. The vehicle is physically partitioned into a motor section, airframe body, avionics bay, and recovery compartment. These sections define the primary assembly units and determine internal volume allocation, mass distribution, and access for integration and inspection. The overview at this stage is strictly geometric and physical, serving the baseline for subsequent subsystem definition. At the subsystem architecture level, the rocket is organized into 4 interacting subsystems: propulsion, structure, avionics, and recovery. Each subsystem has a defined functional responsibility and a bounded interface to the rest of the vehicle. Propulsion defines the acceleration environment, structure governs load bearing and alignment, avionics manages sensing and deployment logic, and recovery enables vehicle reuse. The central architecture principle is limited coupling. Subsystems interact only through well-defined mechanical, electrical, and operational interfaces. This separation allows independent verification of subsystems prior to full system integration. The propulsion subsystem is based on an impulsor-class solid rocket motor following published experimental designs and validated test data developed by Richard Naka. The motor is fueled with potassium nitrate dextrose propellant and is selected to meet the required total impulse for the target vehicle mass and apogee. Rather than pursuing cost-to-motor development, the propulsion design leverages established motor behavior to define acceleration level and ascent duration. Static firing is used as the primary vehicle verification activity, providing confirmation of thrust, chamber pressure, and closure integrity, while post-test inspection is employed to assess nozzle erosion and structural condition. This approach allows propulsion-related uncertainties to be characterized experimentally and integrated consistently into an overall vehicle design. Motor closure is implemented as a bolted joint rather than a snap reconfiguration. 4 circumferential bolts are used to improve failure predictability. Axial thrust loads are transferred through bearing at the bolt heads rather than through the threads, reducing the risk of a motor case failure due to concentrated loads. Lower grade bolts of deliberately reduced strength are selected so that in an overpressure condition, failure occurs in the closure hardware rather than the motor casing. Bolt preload is neglected at this stage, and the connection is treated without reliance on controlled torque. This approach allows closure behavior to be evaluated directly through testing rather than inferred from assumption. Post-test inspection focuses on bolt deformation and seating condition as a direct indication of load transfer and closure performance. Aerodynamic stability is evaluated in open rocket using Barrowman-based models appropriate for slender fin vehicles. The configuration is sized to achieve a static margin of approximately 2 calibers at liftoff, providing stability tolerance to uncertainties in mass distribution and aerodynamic coefficients. This margin is selected to balance competing effects, avoiding insufficient stability that may lead to divergence or weathercocking, while limiting drag and fin loading penalties associated with excessive margin. Stability sizing is treated as a baseline design constraint rather than an optimization target. The analysis directly informs integration decisions including internal mass placement, motor position, and fin geometry. Sensitivity checks are performed by perturbing mass and fin parameters to verify that positive stability is maintained under assembly variability. The resulting configuration ensures stable behavior through rail departure, boost, and early coast. CFD is applied only when it directly informs design decisions. Steady-state compressible simulations are performed for internal nozzle flow to examine gas expansion and internal pressure distribution relevant to structural interfaces. The results are used to verify consistency and analytical expectations by confirming chamber-to-exit pressure trends and assessing the plausibility of assumed operation conditions. CFD is not employed for thrust optimization or external aerodynamic prediction. External flow analysis is omitted at this stage because the vehicle operates in the subsonic regime where global aerodynamic loads are adequately captured using analytical and semi-empirical methods. The primary CFD outputs are wall pressure distribution and integrated loads on nozzle adjacent components, which are used to cross-check structural pressure assumptions. Numerical settings are selected to ensure stable convergence and conservation. The structural concept is based on a thin-walled cylindrical airframe designed to carry axial thrust loads and bending loads induced by aerodynamic side forces. Stiffness is prioritized to maintain alignment of internal components and to ensure reliable recovery deployment under combined acceleration and vibration environments. Structural evaluation focuses on representative boundary conditions at the motor interface, airframe joint, and avionics mounting locations rather than detailed material level optimization. Load cases include axial compression from thrust combined with lateral loads representing aerodynamic bending, with conservative magnitude applied to reflect uncertainty. Reported outputs include global deflection, peak stress at joints, and localized stress concentration. These results are used to identify where reinforcement is required to improve robustness, with mass optimization deferred to later design stages. Recovery is implemented as a single-stage parachute system deployed near apogee to ensure safe descent and enable hardware use. Recovery is treated as mission critical because deployment reliability dominates overall risk in small sounding rockets. The design therefore emphasizes robust mechanics, clean routing, adequate injection energy, sufficient volume margin for packing variability, and interfaces that are tolerant to vibration and acceleration. Deployment timing and arming logic are coordinated through avionics, but the mechanism is designed to function without fragile tolerances. Verification is staged. Ground deployment tests with representative packing, environmental checks for friction and binding, and inspection after each test. Performance requirements are expressed as representative deployment success over many trials. This subsystem drives packaging constraints and stiffness requirements upstream. The project is currently at the completion of the preliminary design and analysis phase, with subsystem interfaces defined and load envelopes established for the first integrated prototype. The next phase is experimental validation, starting with static motor testing to confirm thrust and chamber pressure assumptions, followed by ground recovery tests to evaluate deployment reliability under realistic packing and hardware tolerances. The dominant risk at this stage are recovery deployment performance, manufacturing tolerance affecting fit and alignment, and uncertainty in aerodynamic side loads during ascent. These risks are addressed through a structured test sequence in which subsystems are verified individually before progressive integration and flight testing. Success is judged against predefined criteria, including measured thrust and pressure within bounds, repeatable recovery deployment, and inspection showing no evidence of progressive damage. In conclusion, the work delivers a coherent vehicle architecture supported by explicit assumptions and targeted analysis. Propulsion selection, stability sizing, and structural concepts are defined to enable practical fabrication, integration, and repeatable testing. Limited CFD is applied only where it informs nozzle interface pressure behavior and improves confidence in internal pressure environments. External aerodynamics are addressed with established analytical tools appropriate to the flight regime. The outcome is a design baseline with clear interfaces and bounded loads, prioritized through static testing and ground validation before flight. Future work follows a validation sequence. Update mass properties with measured hardware, refine stability with as-built inertia, and extend analysis to external CFD or aeroelasticity only if test evidence motivates it. Clear acceptance criteria guides each step. This keeps scope aligned with available resources. Thank you for your time and attention. I'm happy to answer any questions.